Welcome to our class. Can you turn on your cameras, please? Okay. So for today, we are going to continue with the transition elements. Okay. Now, Charlotte, is that your younger sister or brother? Younger sister, right? Wow, she's so cute. Okay. Welcome to our class, little sister. Okay, so today we're going to continue with our lesson about. Oh, do you want to join our class?
Do you want to join our class?
Hi.
Yes.
Oh, yeah.
Okay, so let's start first. Okay, let's continue with the transition metals. Okay. So basically, okay, we know that one of the characteristics of the transition metals is that when they form a complex with water, okay, they form different colors, okay, different colors of solution. Okay, now so let's look at the colors of the transition metal. Okay, how do we see color? Now, basically, we have discussed this when you were in grade 10, and I believe that in the physics class, you already discussed the visible spectrum, right? So most transition metal compounds appear with different colors. Okay, that's one of exciting about these transition metals. It's very unfortunate because we cannot really do the experiments now in the laboratory. That's why I have given you the video, okay, the video yesterday, for you to be able to determine the different colors of the transition metals. Okay, now I remember when I was in the university, the first exercise that I have done, the first laboratory exercise that I have done in my entire university life was about the transition metals. Okay, so and I was so fascinated because there are lots of different colors. Okay, now so most transition metal compounds appear colored. This is because they absorb the energy corresponding to certain parts of the visible electromagnetic spectrum. Now we know that the color that can be seen, okay, is actually made up of the parts of the visible spectrum that, okay, which are not absorbed. Okay. So for example, a red compound will absorb all the frequencies, at the of the spectrum, okay, and then the red will be reflected through the eyes. Okay, we know that already. Now, if the sample is colored blue, then all the parts of the visible spectrum will be absorbed by the solution, and the blue one will be reflected to our eyes. Okay, so we know that already. Now, what happens when light is absorbed? Now, in transition metal ions, the D sublevel is only partially filled. Now, I remember I gave this question in the CA. Okay. Now, this means that the electrons can move between D orbitals. That's the reason why, okay, this is the reason why different transition metal solutions have different colors. Now, in a transition metal complex, the relative energies of the d orbitals change. Okay, so electrons can be promoted to higher energy orbitals, And when the electrons are promoted to a higher energy orbital, what happens is that they absorb light energy of a particular frequency. And then this frequency depends on the precise difference in the energy between the d orbitals. Okay? And then when they return back to their original position, then they will emit the light. Okay? And that is the color that can be seen. Okay? So let's look at this. How do ligands or the ligands affect the energy levels of d orbitals? Okay. So the three d orbitals in a free ion all have the same energy. Okay, they have the same energy. Now, ligands cause the d orbitals to split into two different energy levels, making electron transitions possible. Okay, now let's see. So, like for example, the copper 2 plus ion has 9 electrons in its 3D sublevel. Now, these are distributed between orbitals of the same energy. And then, in an octahedral complex, there will be a repulsion from the ligand electron, causes the copper ion 3D orbitals to split into two energy states. Okay? Now, these orbitals have less energy and two orbitals have greater energy. Okay, so three orbitals have less energy and two orbitals, okay, will have greater energy. So these um, the orbitals will split into two. Okay, and then an electron. Okay, look. Okay, an electron can be promoted from the lower energy orbital to the higher energy orbital by absorbing a photon of light of a frequency which is equivalent to the difference in the energy between these two orbitals. Okay. And then, okay, now for a tetrahedral complex, that's for the octahedral, no? Now for the tetrahedral complex, the ligands cause a different pattern of energy splitting in the d orbitals.
You're still muted, sir. You're still, sir.
Oh my. Okay, I was muted. Okay, that's the reason why I was asking you if you have questions and you no one is answering me. Okay, so, sorry for that. Okay, so let's go back. Can you hear me now? Can you hear me
Yes,
now?
Yes.
Mr.
Oh, that's good. Okay, so I've been talking. So in which part have I lost my sound? In which part?
Since you disconnect.
Oh, when I was disconnected. Okay, wait for a while. Huh? Okay, I'll just stop my video. Huh? Okay. Okay, so you can hear me clearly, right?
Yes.
Okay, good. So let's start again. Okay, now what we're talking about is about why do the orbitals change in energy? Okay, and in this change of energy, light, okay, this change in energy also causes the change in color of the different ligand complexes. Okay, now let's say we have copper 2 plus ion. Okay, now we know copper 2 plus ion has 9 electrons in its 3D sublevel, and they are distributed, okay, in the orbitals of the same energy. Okay, we know that already. And then in an octahedral complex, okay, what happened is that there is this repulsion from the ligand electrons causes this copper ion 3D orbitals to split into two. Okay, it's been split into two. Okay, two energy states. Now, three orbitals, 1, 2, 3, have less energy, while these 1 and 2 orbitals, have greater energy. So there's this difference in the energy. No? Now, an electron can be promoted from lower energy orbital to a higher energy orbital by absorbing the photon of light with a frequency which is equivalent to the difference in the energy between these two orbitals. Okay, so energy is absorbed. Photon of light is absorbed. Okay? Now, in an in a tetrahedral, no, so this is in the octahedral, right? Now, in a tetrahedral complex, ligands cause a different pattern of energy splitting in the d orbitals. Two of the orbitals have less energy, while three of them have greater energy. Okay, so this is for the tetrahedral complex. So what will happen is that, okay, let's go back here. Okay. So here, okay, the amount of energy is less. Okay, so photon of light, the frequency of the photon of light here is also less. Okay, so it will also appear with different color. Okay. Okay. So for our purpose, no, so this will be the equation relates the energy difference, okay, between the orbitals and the frequency. No, we have this already when you were in grade 10. Okay, and therefore color of the light absorbed by the complex. Okay, so the energy difference will determine the color difference, no, in the ligand complex, in the in the ligand complex that we have. Okay. Anyhow, don't you worry. You know, we're not going to compete for the change in energy anymore. No, we have done this already. But here, no, I just want to tell you that the color, okay, depends on the difference in the energy level of the split d orbitals. Okay. Okay. Now, what are the factors that can affect the colors of the complex? Okay, now the color of a transition metal compound is determined by, as we already know, the difference in energy between its d orbitals. Okay, so we know that already. Now, this can be affected by several factors. Okay, now the difference in the energy between its d orbitals can be affected rather by several factors. And what are those? First, size and the type of ligands. Of course, no. Um, just like what we have seen, if it is tetrahedral, in the end, the difference in the energy is smaller compared to the octahedral with larger difference in the energy. Strength of the metal ligand bonds. Okay. Complex shape. Okay, just like what we had last time, the tetrahedral and the octahedral. Also in the coordination number of the ion. And also it depends on the oxidation state. Okay. So here, if we have chromium 3 plus, it has different color with nickel 2 plus, which is also different from the color of iron 2 plus, which is also different from iron 3 plus. Okay. So the colors of the metal, rather the color of the transition metal complex would be definitely will be determined by the difference in the energy between its d orbitals. And this will be affected by the size and type of the ligands, the strength of metal ligand bonds, complex shape, coordination number, and the oxidation state. Okay. I think there was. I would like to open up this. No, it seems that some of you are still copying directly the answers, no, from some references or resources. Okay, that's why, you know, if you will notice your scores are not that really good because you just copied it directly. I have already mentioned to you that when you refer, okay, from reference, because I cannot prevent you from doing that. I know that some of you are still just copying the answers from the references. Now, it would be better if you will use your own words. Sad to say, I have also noticed that there are some students who also copied the work of their classmates, and that is really bad. Okay. Now, if so happen, if 2 or 3 or 4 of you will have the same answers in the test, all of you will have deductions. Now, it so happened that I have found out that even the wrong spelling was copied by the classmate or classmates. So how can I say that you didn't copy it if even the wrong spelling of a certain word was being copied? No, um, it's very unusual, no? to write or to type a certain word, you misspelled a certain word, and all of you misspelled the same word. So it's very unusual to happen. Okay? So that's one of the proofs that one of the proofs that some of you are still not showing your integrity during the test. Anyhow, now colors of complexes. Now, a transition metal will appear different colors in complexes with different ligands. Okay, example, if we have copper 2 plus, okay, the aqueous copper, it has this color. I think this is color blue. I am so sorry, one of my problems really when I'm doing experiments, especially when I was still studying, is that I am really confused with the colors. Okay, so yeah, so change in color sometimes I got mistakes because sometimes I didn't see that there's a change in color, especially if the change is of colors green from green to red or red to green. It's so difficult for me to determine. Okay, then of course, which is different from the calcium tetrachloride ion. Okay, I think this is green. If not red, then it's green. This blue, this is green, if I'm not mistaken. Okay, now let's try to do this one. Let's answer the true or false questions. Okay, but before that, do you have any question before we proceed? No question? Okay, now let's try to answer these true or false questions. Let's start with Yeski. Read the question number 1 and answer.
The orbital in free ion have different energies. True.
Are you sure?
Yes.
Final answer?
Uh,
Okay, next, number 2, Wildy. Read and answer. Question number 2.
Electrons in the orbitals can only be promoted if there are unfilled spaces in the orbitals. Um, False.
False. Final answer?
Yes.
Okay, next, number 3. Let's have Funny.
A blue compound absorbs light from the blue parts of the spectrum. True.
Are you sure that the blue compound absorbs light from the blue parts of the spectrum?
False.
Okay, final answer?
False.
Okay, next. Ong, number 4.
The color of a transition metal compound depends entirely on the oxidation number of the metal ion. True.
Depends entirely on the oxidation number.
Hmm. False here.
Are you sure it's
False,
false?
false. Yeah.
Okay, then we have, oh, Nadia's not around, right? She is sick. Okay, Melly, number 5. Melly, number 5, please.
Yes, Mister.
Number 5.
Fusion between the electron and the electron of the orbital. Okay. True.
True. Are you sure?
Yes.
Now let's see. Let's see if your answers are all correct. Oh, okay. Now, the D orbitals in free ions have different energy levels. No, they have. They are in the same energy level, right? Okay. And electrons in the orbitals can only be promoted if there are unfilled spaces in the orbitals. Of course, yes. This is true. Okay, so this one is true and this one is false. Okay? Okay, so remember, no? The d orbitals in free ions have different energy levels. No, they are in the same energy level. Okay? Now, for number 2, electrons in d orbitals can only be promoted if there are unfilled spaces in the orbitals. Of course, if there are no free spaces, so how can the electron be promoted? Okay? And then blue compound reflects light from the blue parts of the spectrum. That is the one that we can see. So it's not absorbed by the, it's not absorbed no, in the compound, but it's being reflected. Now, color of transition metal compounds depends not only with the oxidation number, but also with several factors like the size and shape of the ligand. It also depends on the complex itself, no? Oxidation number, of course, coordination number as well. No, it's not only entirely on the oxidation number. And of course, repulsion between the ligand and metal electrons can cause the d orbitals to split into 2 energy levels. Okay? Try to remember these points. Okay. Do you have any question? Is there any question before we proceed? Okay, none. Okay, let's proceed. Now, how do we determine the concentration of the complexes? Okay, now to determine the concentration, now we can use the ultraviolet spectroscopy. Okay, now I just want to share my experience with the UV spectroscopy. When I was still a student, I was working as an assistant in the laboratory. So I work and at the same time I study. Okay. Now, it so happened that we are dealing also with the concentration of the ions. We were used to examine the content of the ions present in the water of different lakes in the Philippines. So I was involved in that study. I was not professionally involved, but I was an assistant. So I was able to use spectroscopy, and it's really nice to use this instrument. Okay. Now, ultraviolet visible spectroscopy can be used to determine the concentration of a transition metal complex solution. Okay, so now actually this is an old type. There is a new type of spectroscopy. No, this is or spectroscope. No, this is an older model. So a UV vis spectrometer passes different frequencies of light through a sample. Now, some of the light is absorbed while the rest passes through. And then a detector measures the absorbance of the sample. Okay, so this is the principle behind the UV vis spectrometer. No? Now, the sample is placed in a cuvette, and then it will be placed somewhere here. If not here, it's over here. So the amount of light absorbed is proportional to the concentration of the absorbing species. This is how we measure. This is how the ultraviolet visible spectroscopy measure the concentration of a sample. Okay, so the amount of light absorbed is proportional to the concentration of the absorbing species. Okay, let's have an example. Now, let's try to determine the concentration of a transition metal compound. Let's say chromium 3+. Okay, so how do we, by the way, this is what you call a cuvette. C-U-B-E-E-T-E, cuvette. Okay, now this is a transparent glass. Okay, and then you have to put your sample inside the cuvette. Okay, supposedly we have chromium. So the absorbance of a solution is proportional to its concentration. Now, take note of that, no? However, you need to generate a calibration graph first. Okay, now, what is that calibration graph? The calibration graph will be your reference. Okay, so calibration graph of absorbance for each complex in order to obtain a concentration value. So you have to establish first your calibration graph. Now, this requires number of solutions of the complex made up to known concentration. Okay, so you have to prepare first, okay, a number of solutions of the complex with known solution. Like, for example, 0.01 molar, 0.1, 0.5, 1, then 1.5 molar. So you have to prepare first the known concentration of the complex for the calibration graph, okay? And then solutions are placed into the spectrometer, okay? So now that is placed in the spectrometer. Okay, yes, Brenda. Okay. Now look what will happen. Now this is the source of light. Okay. Different frequencies of light are directed at the sample in turn. Now the absorbance at each frequency is measured, and the highest absorbance is plotted on the calibration graph. Okay, let's see. Okay, so that's what happened, no? Now, each solution of known concentration is tested in turn, and their maximum absorbance at the relevant wavelength is recorded. So whatever is the absorbance, okay, that will be determined in each of the concentration, it will be recorded. Okay, so meaning to say, those values will be the reference value for each of the concentration. Then the measurements are recorded on a graph of maximum absorbance. Okay, this is the maximum absorbance versus the concentration. Okay. Now this is your calibration graph. Now, if you have a sample of unknown concentration, okay, you have to place that in the spectrometer and test it. Whatever is its absorbance, the absorbance value, let's say the absorbance value is somewhere here. Okay, so you have to mark on the graph, and then an estimate of the concentration can be read off at the x-axis. Okay. Now, before, I remember we used to have the manual. I mean, manually we do this, especially during the calibration time. Now we have to really graph it manually. But nowadays, okay, there are spectrometers that are connected already to the computer, and it will be processed. Okay, so You don't have to do it manually. It will be um, shown by computer. It will be processed by the computer. Okay? So this is how we measure the concentration of a transition metal. Now, so first, we have to establish our calibration graph, okay, by taking the highest absorbance value of known concentrations. And then after that, okay, you have to put your unknown and plot the absorbance of your unknown on the graph, and then you can just determine the concentration by reading off, okay, through the x-axis, okay, which is the concentration. Is there any question? None? Okay, let's move on. Okay, so improving the UV-based spectroscopy. Some transition metal complex ions have a very pale color. Actually, this is also my problem. When the solution is pale, oh my goodness, I can't really determine the color. So accurate quantitative determination of the concentration of these solutions rather, is so difficult because the difference in the absorption between the different concentration is too small. If the color is pale, it only means that the concentration is less. So replacing the ligands in a complex changes its color. Now, this can be increased absorption of the transition metal species, allowing lower concentration to be analyzed using the UV-based spectroscopy. In other words, you can change the ligands that is connected to your complex, okay, so that it will have a higher absorption. Okay, you can do that. No? You can just, like for example, no, you have copper in aqueous solution, or rather, let's say copper in the aqueous solution, which has a lesser concentration of copper. So you can use the tetrachloride, no, to combine with your copper, to form another color of the ligand or the leader complex that can give you a that can give you a strong color, so that the color, or rather there will be an absorption or higher absorption of the transition metal species. Okay, if you have a darker color, then of course can give you higher absorption. Now, another way is, like for example, we have iron 2+, iron aqueous solution. Now it has a pale green color. Now, if the water ligands are replaced by other types of ligands, a much stronger colored solution is produced. And then the absorption values increase by 10 to the third power. So allowing analysis of lower concentrations to pursue. No? So like for example, okay, so we just replace here the ligand. Okay, sorry for that. Okay, so it will give you a stronger color where you can determine the concentration of your ion. Okay. Now let's move on to the hydrolysis reactions. Okay, let's move on to the reactions of these transition metals. Okay. So transition metal salts, okay, dissolve in water to form the aqua ions. Okay. Now basically, no, if you notice in some of our chemical equation, okay, we use the word aqueous, right? To determine the state of the matter of a solution. Now, basically, the aqueous solution is just the ion plus, or in the with the aqua complex, or rather ion and aqua complex. Okay, so to form aqua ions, complexes with water molecule ligands, some of these aqueous complexes are acidic. Now, for example, the ferric aqua ions, or ferric aqua complex, this one. Now, this is acidic because the ion triple ion is strongly polarizing, and it weakens the oxygen hydrogen bonds in the water ligands. Okay. Now, the complex ion releases hydronium or hydrogen ion, producing an acidic solution. So, when iron is in the aqueous state or in the aqueous solution, now this forms an acidic complex. Why? Because iron 3 plus ions are strongly polarizing, and this makes the oxygen and the hydrogen bond to break, okay, in the water ligands. Okay, so if hydrogen is present in the solution, then it only means that the solution is quite acidic. Okay? Now, this process of breaking the oxygen and hydrogen bond is called hydrolysis. Okay? Because the water molecule is being split. Okay? Now, the general equation for this reaction is the metal aqua complex plus water. It will give you this complex plus, okay, the formation of the hydronium ion. Okay? So if there is the presence of hydronium ion in the solution, it only means that the solution is acidic. Okay? Now, M here stands for any metal, no? I mean, any transition metal. Okay? The M here stands for any metal or transition metal ion. Okay, question? So again, no? Okay. Now, if the ion or metal ion is polarizing, it will break or split the water molecule into releasing the hydrogen atom, no, in the bond, creating the free hydrogen ions. So it will create, if there's the concentration of the hydrogen ion is high in the solution, it creates an acidic solution. Okay, and this is our general equation for the hydrolysis of the water in the aqua ion complexes. Now, why are some aqua ions less acidic? Okay, why some of the aqua ions are less acidic compared to the others? Now, suppose we have a solution of iron 3 plus, which is highly acidic, whilst a solution of iron 2 plus is only very weakly acidic. Now, this is because the polarizing power of the metal ion depends on its size and charge. Okay? So, the acidity of the aqua ion solution will be dependent on the size of the metal ion, and also it will depend on the charge of the metal ion. So smaller, more highly charged metal ions exert a greater polarizing effect on the water ligands, so that more oxygen-hydrogen bonds will break, releasing more hydrogen ions. So it will become more acidic, right? Okay. So if the cation is smaller and with higher charge, then it will become more polarizing to break that oxygen-hydrogen bond, okay, making the hydrogen ion to be free. Okay. Now, as a general rule, any metal or transition metal 3+ ions are significantly more acidic than the M2+ ions. So for the copper, we have copper plus and copper 2+. So copper 2+ ion will be great. It will become highly acidic compared to the copper plus ions. Okay. Okay, is there any question so far? Do you have any question? Question? Do you have any question? Teletubbies, do you have any question?
No, sir.
None. Okay, are you sure? Okay.
100% sure.
100% sure. Okay. Okay, so let's continue. Let's try to do this one. Okay, write down, copy, and write down. So order these complex ions by acidity. Okay. Write down your answers in your notebook. Order these complex ions by acidity. So we have here manganese, aqua complex, copper, aqua complex, ferric, aqua complex, vanadium, aqua complex, and chromium, aqua complex. Okay, arrange them in order of acidity, with the most acidic at the top and the least acidic at the bottom. Okay, look at the ionic radius of manganese 3+. It's 72 picometers. For copper 2+, is 87 picometers. For iron 3+, is 69 picometers. For vanadium is 93 picometers. And for chromium 3 plus, 75.5 picometers. So what did we say? Which one will become more polarizing? Is it the bigger radius, the bigger ion, or the smaller ion? So again, magnesium 3 plus has 72 picometers. Copper 2 plus has 87 picometers. Ferric ion has 69 picometers. Vanadium 2 plus has 93 picometers. And chromium 3 plus has 75.5 picometers. Okay, now order these complexes ions by acidity. Number 1 should be the highest, and number 5 should be the least acidic. Are you done?
Yes, sir. Yes, sir.
Done?
Yes, sir.
Now, type the ion in the chat box in order. Let me see your answers. Type in your answers in the chat box. Okay. Leroy, 53142. No, write down the ion, not the number. Huh? The ion. Write down the ion.
Oh.
Starting from the most acidic, then to the least acidic. Just the ion. You don't have to type in the whole complex, just the ion. Write down. So you should type 5 answers in order. I mean, type ions. So Yeski has iron 3 plus, manganese 3 plus, chromium 3 plus, copper 2 plus, vanadium 2 plus. That is Yeski's answer, which is almost the same with Will D. You have typed the elemental elemental symbol, not the ions. Will D. Some more answers. Abel, same with Yeski. Charlotte, same with Yeski. Okay, Leroy, elemental symbol also. And Brenda, same with Yeski. Okay, Galen has. Okay, do not forget the symbol, yeah, the 3 plus Galen. Okay, now let's try to check if your answers are correct. No? Okay. That is right. No? So, okay, the most acidic is the iron aqua complex, 3 plus, followed by the manganese aqua complex, then chromium aqua complex, then copper aqua complex, and last is the vanadium aqua complex. Okay. 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 Now just try to remember. Okay. Now remember that the smaller the ion and with higher charge, it will become more polarizing that will create or it will facilitate the process of hydrolysis between the oxygen and hydrogen bond. Okay, splitting the water molecule, releasing the H plus or the hydrogen ion, okay, in the solution, and that makes higher concentration of the hydrogen ion means that it is more acidic. Okay? Okay, let's move on. Okay, so a series of hydrolysis reaction can occur until the overall charge on a complex is zero. For example, in a transition metal of 2 plus ions, with 2 hydrogen ions are removed. Okay, so first, one of the hydrogen ion is removed, and then after that, another hydrogen ion will be removed. So until the overall charge on a complex becomes zero. Okay, so in other words, if it is 3 plus, so there are 3 hydrogen ions that will be removed. Okay, so here, 3 H plus ions are removed from the transition metal with 3 plus ions. Okay, so 1, 2, 3. That makes sense, right? If it has a higher charge, meaning 3, or it means that more hydrogen ions will be removed. Okay, creating a higher concentration of hydrogen ions in the solution. Okay. Now, how about the reaction of the transition metals with bases? Okay. Now here, if a base such as ammonia or hydroxide ions is added to a solution, just like the experiments that we have seen yesterday, okay? So if base is added to a transition metal aqua ions, H plus ions are removed from the water ligands until there is no overall charge on the complex. Okay? So here, until it becomes, the overall charge will become zero. Okay? The final product is uncharged and insoluble metal hydroxide that forms a precipitate. Mean to say, when you put a base in the complexes, there will be an insoluble metal hydroxide that will be formed. Okay, so precipitate of metal hydroxide will be formed. Okay. Like for example, if you have a copper aqua complex and you added ammonia, then therefore it will produce copper hydroxide, precipitate of copper hydroxide. Okay. Now, this reaction occurs in a series of steps, depending again whether the metal is a 2 plus or 3 plus ion. Okay. Now, reactions with carbonate ions. Okay. Like for example, sodium carbonate acts as a base with M3 plus aqua ions to produce hydrated metal hydroxide. Hydrated metal hydroxide. Okay, hydrated meaning there's a presence of water molecule, no? So, okay, but in the solid form. So this is, okay, like for example, we have a chromium aqua complex combined with a carbonate. It will produce, okay, chromium hydroxide in the hydrated chromium hydroxide, carbon dioxide, and water as other products. Okay, however, adding sodium carbonate to M2 plus ions produces an insoluble metal carbonate. Okay, so if we add, okay, take note of the difference. If we add carbonate ions with a transition metal 3 plus aqua ions, metal hydroxide will be formed. Hydrated metal hydroxide. However, if we add sodium carbonate to M2 plus ions, then it will produce metal carbonate, insoluble metal carbonate. Now the M2 plus ions are less acidic, and carbonate ions are unable to remove all the protons from the water ligands. So they displace the ligands instead. Okay, so this is our equation for that. Okay. So there's just the displacement of the water ligand, or rather water ligand, no, in the complex. Okay, so carbonate ions displaced the water molecules, forming chromium carbonate. Okay, okay, so that's the difference, no, with the reaction with carbonate ions. Okay. Okay, questions? Questions? Okay, if there's none, okay, let's have our 5-minute break first. Okay. Okay, turn on your cameras now. Okay, in the yesterday's activity, you have seen the actual reactions of the complexes together with the base, right? You have seen the precipitates, okay, the precipitate of each of the complex as they react with, I think they use sodium hydroxide if I'm mistaken. Okay, now let's try to have a simulation of the reaction. Okay, I'm going to show you the simulation of the reaction. Can you hear me, right? Okay, can
Yes,
you hear me?
sir.
Okay. Let's try to look at the simulation of the reaction. Okay. Okay. So adding bases to complexes, okay, will give us the following results now. So aqueous transition metals, the aqua ions, react with aqueous bases, including sodium hydroxide, ammonia, and carbonate ions to form colored precipitates. Now, when say precipitates, these are the solid precipitate, yeah, solid part of the solution, no? Okay, now let's start with chromium. Let's see now what will happen. No? If we use chromium and we add ammonia. Okay, so this is the color of chromium, the chromium aqua complex. When we add ammonia, let's see what will happen. Okay, so here, chromium added with ammonia create a metal hydroxide. Okay, this is the metal hydroxide. Okay, so let's try to look if chromium is added with sodium hydroxide. What will happen? So again, in this case, okay, chromium hydroxide has been formed, no, from this solution, no. So you can see the solid precipitate, no. Okay, this is the color. Now let's try to look if we add sodium carbonate. So again, in this case, if we add sodium carbonate, okay, there is also the formation of chromium hydroxide there, and also the formation of carbon dioxide. And the evidence is the bubbles that is coming out from the solution. Okay, so this is for chromium. Okay, now let's try to look at the reaction of the manganese aqua complex. Okay, let's try to add. Okay, remember, no, manganese 2 plus, no? So let's try to add ammonia. Okay, look. Here, there's the formation of the precipitate of manganese hydroxide. It's solid, no? It's precipitate. Let's try to look when we add sodium hydroxide. Okay, as you can see, again, manganese hydroxide is formed, no? Solid manganese hydroxide. Okay. Let's try to check whether manganese 2 plus will form precipitate when added with sodium carbonate. Okay, in this case, the precipitate is manganese carbonate, which is also precipitate. Okay, which is also in the solid form. Okay, now the color is this color. Okay, let's try. Let's try aluminum, the aluminum aqua complex. Okay, so it's this color for aluminum. If we add sodium hydroxide, ammonia rather, it will form a white precipitate, which is aluminum hydroxide. Okay, white precipitate of aluminum hydroxide. Now let's try to check if what will be the precipitate if we use sodium hydroxide. Of course, it's sodium hydroxide, then definitely it will form aluminum hydroxide. And it is soluble here, no? So it's aqueous. Okay, it's soluble. Okay. Now, what if we use sodium carbonate as our base? Again, sodium hydroxide is formed, and also the presence of carbon dioxide. Okay, the presence of carbon dioxide here. Okay. Let's try to check copper 2 plus. Okay, this is the solution of copper 2 plus added with ammonia. Oh, it produced blue, right? Okay. Blue copper hydroxide precipitate. Okay. Now let's try to use sodium hydroxide. Okay. It also produced copper hydroxide precipitate. Now let's look at the precipitate that will be produced by the complex copper complex with sodium carbonate. Oh, here calcium carbonate, okay, is formed. No carbon dioxide. What happened here is that the ligand water in the complex is being displaced or replaced by the carbonate ion. So that's why there's the formation of copper carbonate, and okay, the water is displaced. The water molecules are being displaced. Okay. Now let's try to look at the iron. Okay, let's try the iron 3 plus first. But we have the yellowish solution here, added with sodium, or rather added with ammonia. Okay, and there's this orange precipitate, right? There's the formation of iron hydroxide. Okay. Let's try with sodium hydroxide. Okay, here there's also the formation of iron hydroxide. Okay. Orange precipitate. Let's try with sodium carbonate. Okay. With sodium carbonate, there's the presence of carbon dioxide as well. Okay. Now let's try to compare it with ferrous ion. Okay. With the Fe2 plus. Okay. Look at the color of the solution, which is different from the iron 3 plus, no? From the ferric ions. Okay, if we add the carbonate, okay, to the Fe2 plus solution, or rather complex, now again, carbonate ions displace the water molecules to form iron carbonate. Of course, and then there's no carbon dioxide. So basically, now what happened is that the carbonate ion displaced the water ligand in the iron water ligand complex. Okay. Let's try with cobalt. Okay, adding ammonia. It will form cobalt hydroxide. With sodium hydroxide, let's see what will happen. Okay. So a very soluble precipitate, okay, has been formed. Okay. And then with sodium carbonate as our base, let's see what will happen. Okay, again, in this case, no, the carbonate ion displaces the water molecule to form cobalt carbonate. Okay, and there is no presence of carbon dioxide. Okay, let's try to look at nickel 2 plus. So nickel 2 plus ammonia will form nickel hydroxide, okay, with this color of its precipitate. Let's add sodium hydroxide. Okay, so still nickel hydroxide, right? Okay, let's try with sodium carbonate. Okay, now for this complex, what happened is that, again, the carbonate ions displace the water molecule to form nickel carbonate precipitate. Okay? So it is clear, no, that if it is, if the ions has a charge of 3 plus, okay, if you add sodium carbonate, then there will be the production of carbon dioxide. Okay. And metal hydroxide will be formed. However, if the charge is 2 plus, it will form metal carbonate. And there's no formation of carbon dioxide. Okay? Okay. I hope that that's clear. Okay? Okay. Now, let's skip this one. Now, there are substances, or there are metal hydroxides that can react as both an acid and as a base. And we know that this is what you call the amphoterics. Okay, the amphoteric, meaning it can react as an acid and also as a base. Okay. Now, for example, we have chromium hydroxide. So chromium hydroxide will react in the following ways. Okay, first, with strong acids. Chromium hydroxide plus a strong acid, it will give you chromium aqua complex, okay, and water. Okay. Now, if we allow to react chromium hydroxide with a strong base or strong alkali, it will create, okay, just like what we have seen earlier, it will create a chromium hydroxide and with water. Okay. So in other case, no, in other words, okay. Now some of the metal hydroxides they can react, okay, as an acid or as a base. No, with strong acid, chromium hydroxide act as a base, while with the strong alkali, chromium hydroxide act as an acid. Okay, so in other words, this metal hydroxide is an example of an amphoteric metal hydroxide. Okay. Okay, let's try to do this one. Let's try to match these terms to their definitions. Okay, let's start with Charlotte. Aqua anion or aqua ion. What's an aqua ion? Charlotte?
A complex with water molecule lichens.
Okay, let me see. Okay, let's see. Hydrolysis. Abel.
Splitting a water.
Amphoteric. Galen.
A substance that can react as both an acid and base.
And Leroy, polarization. Leroy Sinta, polarization.
The effect of one species on the electron cloud or another.
Oh, hey, it's me. The effect of one species of the electron cloud of another.
Okay. 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 So next week, we are going to discuss about the ligand substitution reactions. Huh? Now, I will encourage you to read your textbook. Okay. So read your textbook and we are going to discuss this. Now, this is also included in the BA. Huh? Okay, do not forget that. And for next week, aside from the discussion, okay, you are going to do also your PA. No, don't you worry, the PA will be very easy. No? It won't spend much of your time. Actually, we can do the PA during our class. Okay, so I will let you open your camera while you're doing your PA. I will announce the PA. I haven't announced the PA yet, right? Not yet, right? Okay, only for the bio, but not for the chemistry yet, right? Okay, so I'm going to announce the PA soon. It will come soon. Okay, do you have any question?
Nice hair, sir.
Thank you for the compliment. Because I'm already tired of shampooing and combing my hair. Now I want, but you know, you can see my scalp. It's kind of loud already. Anyhow, thank you for the compliment. Okay, one of my friends, oh no, Mr. Julius, he told me that I look like a goon or a bad person with my hair. That's what he said. Okay, and he said that he was afraid of me because of my hair. Anyhow, okay. So, do you have any question before we end our class? None, right? Now, please, please, I'm begging you, start studying for the examination. Huh? Okay. So far, no. Based on the CAs, the two CAs, no. You are in the average. Okay. So, majority, basically, if your grades is in the verge of failing, and if you fail the BA, your grade will also fail. So please study, no? Okay, I cannot assure you that I will make a very easy BA, but definitely all the lessons that we have taken up will be added or will be included in the BA. By the way, have I already shared the materials? The PowerPoints, have I already shared for the chemistry?
Oh yeah, sure.
Yes. Okay. So start
Okay.
reviewing. Reviewing for your BA. Okay. Now, if you don't have any questions, then see you next week. Bye bye. Thank you for coming. Bye bye bye. Okay. God
Yes, sir.
bless. Bye bye. God bless you. Nelly, done.